Good morning all of you. Myself KVS Murthy, working as Assistant Professor in Department of CSE, SRKR Engineering College, Formal Languages and Automata Theory. Today I will explain about pumping lemma for regular languages and its applications. The main objectives of this class are to understand the pumping lemma for regular languages and its applications. Before going to define the pumping lemma, we have to remember three important points. Number one, all the regular languages can be represented by using finite automata. And other one is the pumping lemma is used to prove some languages are not regular and it cannot be used to prove some languages are regular. Always pumping lemma is used to prove certain languages are not regular. It cannot be used to prove some languages are regular. This is the statement of the pumping lemma. Let L be any infinite regular language, then there exists a constant n depending on L such that for every string z in L mod z greater than or equal to n, then we can divide such z into three substrings z equal to uvw such that the following three conditions are true. Mod v greater than 0 or v not equal to epsilon, mod uv less than or equal to n, and the string u v power I w is also in L for all I greater than or equal to 0. That is, u v power I w belongs to L for all I greater than or equal to 0. These three conditions are called necessary conditions for a language to be regular. Now coming to the proof of the pumping lemma, let L be any infinite regular language. We know that for every infinite regular language there exists a finite automata accepting all the strings in it. And we also know that such a finite automata has some finite number of n states. This n can be taken as the constant and it is also called the pumping length. Now we have to consider a string z in L. Let z equal to a1, a2, a3 and so on am belongs to L. Now what is mod z? Mod z is greater than or equal to n. Greater than or equal to n. Here that n is the constant of the pumping lemma. Now let us assume that q naught is the initial state of our automata m which accepts L, and if we take delta of q naught comma z, we will end our transmission path at the state qf, which is a final state because the string z is already in L. Now we observe that how many states are there in the path from q naught to qf for the string z. We observe that this path has minimum n plus 1 states. Minimum n plus 1 states. Now we have to note that there are minimum n plus 1 states in the path for the string w. Already our automata has only n states. So we can easily say that from the pigeonhole principle, all the n plus 1 states in the above path are not different. So at least two states must be identical in the above path. Let qi and qj are the two identical states. Now we can divide our z string into three substrings. Using the first part of z, we can move from initial state q naught to qi. Using the second part of the string, we can move from state qi to qj. Both qi and qj are same. And finally, and by using the third part, we can move from qj to the final state qf. In such way, the string z can be divided into three parts, and those three parts are known as uvw. So here let u equal to a1, a2 and so on ai, let v equal to ai plus 1, ai plus 2 and so on az, and w equal to az plus 1, az plus 2 and so on am. We observe that mod v greater than 0 and mod uv less than or equal to n. And now the following diagram shows the transmission path for the string z in the automata. Q naught is the initial state. After applying the substring u, we can move from q naught to qi. Now after applying the substring v, we can move from qi to qj, both are identical states. And finally, after applying the third part w, we can move from qj to the final state qf. Here we also observe that if the substring v is not applied, even the string uw belongs to L, because the string uw terminates at the final state. And similarly, if the substring v is applied once, the resultant string is uvw, that is also ending with final state, so that is also belongs to L. Suppose if the string v is applied two times, the resultant string is u v square w, then also it terminates at the final state, then also u v square w belongs to L. In that way, u v to the power of I w is also belongs to L. So the third condition for the pumping lemma is also existing, hence the theorem. Now coming to the applications of pumping lemma, the pumping lemma can be used to prove some languages are not regular. In order to prove any language is not regular, first of all we assume that such language L is regular. So the pumping lemma will hold. Now the language L is accepted by a finite automata with n states. Now we have to choose a string z such that mod z greater than or equal to n. Now by using pumping lemma, we can divide z into three parts uvw with the two conditions mod v greater than 0 or v not equal to epsilon and mod uv less than or equal to n. And finally, our target is to find an integer I such that u v power I w not belongs to L. According to pumping lemma, u v to the power of I w must be belongs to L for all values of I. If we find an I value such that u v power I w not belongs to L, that is a contradiction to our pumping lemma, and so our assumption is wrong, hence the given language is not regular. In this way, pumping lemma is used to prove some language L is not regular. And now the problems on pumping lemma. Let L equal to a power n b power n such that n greater than or equal to 1 is not regular. We have to prove that the language L is not regular. So this the given L is a power n b power n such that n greater than or equal to 1. If we expand the language, what are the strings in this? L equal to ab, a square, b square, a to the power of 3, b to the power of 3, a to the power of 4, b to the power of 4, and so on. Now we assume that L is regular, so our pumping lemma can hold. As L is regular language, there exists a finite automata that accepts L, and such a finite automata has n states, and such n value can be treated as the constant for that language. Now we have to take a string z in that language. Let z equal to a power n b power n belongs to L. Now what is mod z? Mod z equal to 2n, that is greater than or equal to n say. Now by using pumping lemma, our z can be divided into three parts uvw. What is u? U is suppose u equal to a power p, suppose v equal to a power q, and suppose w equal to a power r b power n. Here we easily observe that p plus q plus r equal to n, and q is not equal to 0, and so mod v is not equal to 0 or v is not equal to epsilon. At the same time, we also observe that modulus of uv is also less than or equal to n. Here n is the length of z. Now let us take I value 2. That means the string u v power I w becomes u v square w. If we find u v square w, that is equal to a power p, a to the power of 2q, a power r, b power n, and the resultant string is not in the form of a power n, b power n, so the u v square w is not in L. That means according to pumping lemma, u v to the power of iz must be in L for all values of I. Here we got a contradiction to that statement. So this is a contradiction to pumping lemma. So our assumption is wrong. Hence the given language is not regular. In this way, we can prove certain languages are not regular by using pumping lemma. Remember, pumping lemma cannot be used to prove some language is regular. It is always used to prove some languages are not regular. Thank you one and all.